its behalf. Now, this is usually used by attackers to bypass security solutions by injecting code into legitimate apps or whitelisted applications, and to access context-specific data, such as taking screenshots or accessing encrypted passwords, such as passwords encrypted by Google Chrome. Now, so what is atom bombing? Atom bombing is it's a new type of injection technique that leverages the global atom table and APCs, which are async procedure calls. And basically, this technique is undetected by common security solutions, or at least it was until we released it in October. And then after that, I'm sure most antivirus vendors kind of rolled out patches to make sure they get this stuff. And also, what's interesting about atom bombing is that it doesn't rely on a flaw in Windows or a bug or some kind of security hole, but it just uses just normal features of the OS in order to get the code injection. So there's no patch that's going to happen or going to be rolled out by Microsoft anytime soon. So it's going to keep working basically for the foreseeable future. Now, in order to understand how atom bombing works, we first have to understand what an atom table is. And an atom table is simply a mapping of 16-bit integers called atoms into strings. And so basically, as an app developer, what I can do is I can call the OS, pass a string to it, and get an atom back, a 16-bit integer. And then whenever I want, I can ask the OS to give me the string back by giving it the atom that I got. So we have two kinds of different atom tables. We have the local atom tables and the global atom tables. Now, local atom tables are less interesting to us because they're accessible to a single process and are completely managed in user mode. And the global atom table is actually very interesting to us because it's accessible across processes and is managed by the kernel. Now, the functions that we can use to manipulate the global atom table are global add atom and global get atom name. Now, the first one receives a pointer to a string and returns an atom, the 16-bit little token that we can use to identify the string. And the second function is the function that retrieves the string and basically receives an atom and a pointer to a buffer and a size. And the size is there just so we don't have any buffer overruns. And then this is pretty neat because what we can do is once we're able to control the pointer to LP buffer that we can see over here, we're able to choose where whatever string we stored is going to be written to. So in theory, if I could somehow call global add atom and store some code in the global atom table, and then somehow force the target process to call global get atom name, and I could somehow control the parameters being passed to this API call, this would enable me to achieve my write what where, because I could choose what to write because I can store whatever I want in the atom table, and I choose where the string is going to be written to. So what we'd like to do is to leverage a mechanism called APC, which is async procedure call. Now, this has been used by malware in the past, just not in this way that we're about to use it. And basically how APCs work is that this enables me to pass a handle to a thread, a pointer to a function, and a parameter to that function, and then that thread will execute that function and receive that parameter that, in theory, I control. Now, the only problem is that the function is of type APC proc, that's its prototype, and so an APC proc expects to receive just one single parameter, and we'd like to call global get atom name, which receives 3 different parameters. So we have a parameter mismatch, and so we can't really control the values of these 2 parameters over here, which really doesn't help us very much. But if we take a look at the underlying implementation of queues or APC, we can see that it actually uses the undocumented system call ntq-apc thread. And what it does is, instead of passing our PFN APC, the APC proc, it passes a pointer to RTL dispatch APC. And this function is actually a function that's found in all Windows processes. And this function will actually dispatch our APC call. So what's interesting about RTL dispatch APC is that its prototype is exactly the same as the prototype of global get atom name. And this prototype is just 3 parameters being passed normally on the stack. So what we could do is we could just cut the middleman and not call QUser APC and not work with RTL dispatch APC, but simply to call the system call directly and then pass a pointer to global get atom name, which will allow me to pass the 3 parameters that I would like. You can see the 3 pushes over here that are the 3 parameters, and then basically I can control the parameters that are going to be passed to global get atom name within the context of the target process. Now, this basically just gives us our write what where, or completes our step 1, because now I can store whatever I want in the global atom table by calling global add atom, and then get the target process to call global get atom name by using the underlying system call ntq apc thread. So once we have our write what where, we'd like to be able to write some code into the address space of the target process and then execute it. Now, for code to execute, it needs to be executable. And we can't assume to find read, write, execute memory within the target process. It's just not going to happen. But we can assume we can find read, write memory that we can write our shellcode to, and then use some return-oriented programming to allocate some executable memory, copy the executable memory from the read-write memory to the newly allocated executable memory, and then finally jump to our shellcode. And then this is actually the ROP chain in detail, and you guys will have the slide deck, so you can check it out later. But we're about to see like a little demo that'll really demonstrate how this works. So now we know what we want to do with the return-oriented programming, but we also need to get the return-oriented programming to work. So what we'd like to do is we'd like to leverage another system call called ntSetContextThread, which receives a handle to a thread and a pointer to a context structure. And the context structure is just holds the values of all the different registers. So what I would like to do is just set the value of the instruction pointer and the stack pointer to point to my ROP chain, and then divert the execution to execute it. However, we don't want to call ntSetContextThread directly, because this system call is quite suspicious. And well, if we have a process that is under our control that's trying to change the context of a thread that's within the address space of another process, then that's very suspicious, and many anti-malware solutions will flag that. So what we'd like to do is we'd kind of like the thread to change its own context, and we can try to leverage APC thread, QUser APC thread again to execute ntSetContextThread, or have the thread call ntSetContextThread on itself by passing the handle to the current thread, and then the context structure that we wrote using our write what where from step 1. Now the only problem here is that generally speaking, a parameter mismatch causes a crash on return, and ntSetContextThread expects 2 parameters and not 3. And so in theory this should lead to a crash. However, in this specific scenario, once the execution gets passed onto the kernel, the return will never take place, because the execution is diverted from the normal execution flow to our new context that we passed in this pointer right here. So there will never be a return, and so there will never be a crash, and so we don't really have a problem here. So let's take a look at the ROP chain in action. Now I've set up my debugger to break just after the execution flow has been diverted. And so we can take a look at the instruction pointer that currently points to allocate virtual memory. And now this function is the function that's going to allocate some virtual executable memory for us. Now the return address is memcopy, which is the function that's going to copy the code from the read-write memory to the executable memory. And this is the 40 right here represents executable read-write. And the memory is going to be stored here where we have zeros right now. So let's let that execute until the return and see it happen. So now if we take a look at the stack again, we can see that where we once had zeros, we now have newly allocated memory. And if we take a look at the protection of this memory, we can see that this is page execute read write, which is 40 as we specified. Now, we can take one more step and see that we land in memcopy. Now, memcopy is the function that's going to copy the memory from the read write to the read write execute memory. And so if we take a look at the stack again, we can see that we have, this is the executable memory that was just allocated and currently contains zeros. And this is where we stored our shellcode before. We can see this is the actual code that's going to be run. But the only problem is that this memory is page read write, so it can't execute, and that's why we need the memcopy. And so we'll let the memcopy execute until the return, and then take a look at where we once had zeros. Now we have some code. And what's left to do is just let the code execute a bit more until we land into our shellcode. Now we can see that our shellcode is executing. If we take a look at the value of EIP, we can see that that's our shellcode. And so what we're going to do is going to let this shellcode execute for a bit until it does something interesting, and that's to call the Windows API winexec, which will spawn a new process. And so let's let this happen and see what it looks like. So one more step, and we can see the calculator pop up. And this basically proves that we were able to inject code into the target process, and the calculator pops up. So back to the slides. What we did is we hijacked a thread to execute code on our behalf. And this thread had a purpose before we had hijacked it. So if we don't restore its execution safely to where it once was, there's no telling what kind of effect we could have on the target app. But what I can assure you what will happen is that it's not going to be stealth. So I'd like to remind you that we're within the context of an APC dispatching. And so somehow the operating system has to return the execution safely, because that's just how APCs work. And so if we take a look at KI user APC dispatcher, which is the function that dispatches the APCs, we can see that it actually stores the original context in a register named EDI, and then dispatches the APC. And when the APC returns, it'll call ZW continue with EDI passed as its parameter to restore the execution safely. In our case, calling the APC causes the diversion of execution to our shellcode, and so this code will never actually execute because there will never be a return to this code. And so what we would like to do is we would like to just back up EDI at the beginning of our shellcode, store it in a temporary variable, and then do our malicious code or whatever we want to do, and then finally call ZW continue ourselves and pass a pointer to the context structure that we backed up from EDI. And then this actually is all that we need to do. And we can go back to our demo and we can see live. We can see this happen. So we'll take a few more steps and we can see that the next thing that's going to be done is we're going to place the backed up value of EDI into EIX, which is another register, push this onto the stack, and then finally call NT continue, which should restore execution safely. And so let's let this execute, and we can see it says the debuggy is running. If we take a look at Google Chrome, which is the injected process, we can see that it works just fine. Now, I don't have internet here, so I can't show you that I can use the web, but trust me, it works. So this works for all normal processes, basically. Now, as for processes that are protected by Control Flow Guard, which MS Paint is an example of those, if we try to inject code into MS Paint, we can see that MS Paint crashes. And if we take a look at the call stack, we can see that actually what causes the crash is a call to RTLP handle invalid user call target, which is a function that belongs to Control Flow Guard. And basically how Control Flow Guard works, it's a new mitigation technique introduced in Windows 8.1 and Windows 10. And it checks and validates every indirect call. And makes sure that the indirect call is made to a valid indirect call target. And basically, so there's the list or a bitmap of valid indirect call targets, and what we'd like to do is have our indirect call target added to that list. And we can do this using NT-set information virtual memory, and we have a whole blog about this on our website. You guys are more than welcome to check it out, which explains how to do this and has code examples. But for our purposes, you can imagine that this system call expects a handle to the process, a call target, and a flag that says mark this call target as valid. And then once we do this, you'd expect this to just magically work, but there's actually one more hurdle we need to get over. And that's that not many people know that actually CFG does more than advertised. And when you enable CFG for a process, it actually enables some stack pivot protection in calls to system calls such as NT-set context thread and NT-continue. Now, this functionality is implemented by calling verify context record, which in turn calls RTL guard is valid stack pointer. So what we'd like to do is we'd like to take a look at these functions and see how this is implemented and see how we can bypass this. And so verify context record simply calls RTL guard is valid stack pointer and passes a pointer to the new value of ESP we're trying to set. And then whatever this function returns will either determine whether we'll return status invalid parameter or status success. So we take a look at RTL guard is valid stack pointer. We can see that what it does is it loads the TB from the E thread. Then from the TB it loads the TIB. Then from the TIB it references the stack limit and stack base of the thread. Sorry, and then checks whether the new value for ESP is between the stack limit and stack base. And if it's below the stack limit or above the stack base, it'll return false. Otherwise, it'll return true. And so what we'd like to do here is we just like to make it seem like there is no stack pivot. And we can do that by querying the stack base and the stack limit of the target thread. And we can do that because they're stored in user mode. And so once we do that, we can just copy our ROP chain to the actual stack of the target thread. And this will make it seem to CFG like there is no stack pivoting going on. Now, some vendors actually demonstrated the prevention of atom bombing by flagging this stack pivot. And this is just an implementation detail, something I'd like to note. It's just an implementation detail, and it can be easily overcome. And we show here some code that actually overcomes this stack pivot problem. And we're going to post this on GitHub within the next few hours, actually. So you can go on and browse it on our repository. And so this is all we need to inject code into CFG protected processes. And so let's see this again live. So you can see we have Paint open here, and we have the command line ready. We also have the process monitor open in the background. And so what we're going to do is just going to inject the code. We'll see the calculator pop up just as before. And if we take a look at the process monitor, we can see that that MS Paint created a new process, and this process is calculator, which is pretty cool. Now, if we take a look at MS Paint again, we can see that it's completely functioning. All of its threads are intact. Nothing is wrong with it. And if the user was using MS Paint while we were doing this, the user couldn't tell the difference. So to sum up, what we did is we took AtomBombing and we split it into 3 different steps. Now, the first step was to write whatever we wanted into the address space of the target process, and we achieved this by calling global @atom to store code in the global atom table, and then we called NTQAPC thread to queue an APC to the target thread, and that APC actually executed global get atom name, and that retrieved the code that we stored within the global atom table. Then step number 2 is execution. We used a little return-oriented programming to allocate some executable memory, then copy the shellcode that we wrote to read-write memory to the newly executable memory, and finally we executed our shellcode. In order to execute the ROP chain or to invoke it, we used QAPC thread again, this time passing it a pointer to ntset context thread, which diverts the execution to execute the little return-oriented programming, and then which eventually leads to the execution of the shellcode. And then finally, to restore execution and to leave no footprints behind, we copy the value stored in EDI, which is the original context. We store that in a temporary variable. And at the end of our shellcode, we call ZW_continue, pass it the backed up value, and this restores the execution, or just lets the OS do what it was meant to do. Now, in order to add CFG exceptions, what we did is we used ntset information virtual memory. And the last step we had to take is to bypass CFG's stack pivot protection. And to do that, all we had to do is just copy the ROP chain to the stack, and then this basically just solves the problem, and there is no issue. So as for Microsoft's response to this, basically the response is that they're not really interested in post-exploitation techniques. And well, we all know that compromise is inevitable, and we do have to deal with post-exploitation techniques. And so the best course of action would be for third-party security vendors would be to hook KI user APC dispatcher and just block calls to global get atom name and to ntset context thread, which nobody should be calling in the first place. So this will never generate any false positives. And this should block any implementation of AtomBombing, because this is the core of it, and there's really no way around this. And that's basically it, guys. If you have any questions, I'd love to address them. Thank you. Any questions? All right.
No one has questions at all? That means this talk was either flawless or you didn't. Yes, thank you. Yes, sir.
Yeah, that's their take on it, and I think that's, yeah. So the question was, what's my take on Microsoft's response? I mean, they basically said that post-exploitation techniques are not interesting, but I think that Microsoft do kind of contradict themselves, because, for example, they say that UAC is actually not a security mechanism. But in fact, they do patch windows to block any UAC bypasses, just like one of our UAC bypasses you guys can see on our blog. And so I think they're just not interested in handing out CVEs and to make a problem where there shouldn't be one. But I think we all know that we do need to deal with post-exploitation techniques because it's interesting and because this does happen out there in the wild all the time. Any more questions? Yeah. No, so they can be used legitimately. They shouldn't be. Yeah, sorry. Yeah, you're right. So the three functions that I said that we should just block. Why not just block them entirely? And why do they even exist if nobody can use them legitimately? So what I meant to say was these functions can be used legitimately, just not within the context of an APC. So during normal programming, you could use these functions, and the first two, which are the global get atom name function. So these functions they're used within the Windows user interface a lot actually, and the other system call it's known to be malicious, but it does have some quite legitimate uses. But there's no way that an APC should call any of these functions. That's just a coincidence that it's possible, and it's something that Microsoft didn't think was possible when they were designing this mechanism. Anything else? It's hard to see if there's anyone up there raising their hand, but I think not. Yeah. Couldn't Microsoft block those from the context of an APC? Yeah, they could in theory. I think they're just not interested in doing it. But yeah, they leave that kind of stuff to the antivirus or next-gen antivirus solutions. But we might see Microsoft making changes to this kind of stuff, in the future, because they are trying to come up with a lot of new mitigation techniques. And for example, they're coming up with this new mitigation technique now that's going to block the ability of one process from changing the context of another process. The privilege itself will not exist for it, and that's something you can set. You will be able to set once this new feature gets rolled out. And so this kind of shows that maybe they are interested in doing something like this someday in the future, but I don't think they're just there yet. Yeah. Can you speak louder? I can't hear you. So a hacker would just need to be able to run code on your machine. There's no need for any high privileges. The limit is that you will only be able to inject code into processes that are within your privilege of accessing. So this basically does not give you an elevation of privilege. This lets you jump from one process to another. Okay, anyone else? All right. Thank you.
Thank you very much, Tal. On behalf of Fitbit and BSidesSF, we would like to present you with a Fitbit Alta and to remind you that motivation is your best accessory. Thank you. Thank you. Thank you. Yeah. It took 3 times, but we got laughs that time. Thank you. There is also a happy hour after all of this, after all the talks right here, hosted by Salesforce. There are still a lot of cookies over there, and there is a Spy Master Challenge going on all day in the Lockpick Village, which is right up that way. Thank you.
So thank you all for coming, and I'm here to answer any questions you may have. And
once again, you can connect with Tal on Peer List, and if you have any